Since ancient times, people have stretched the boundaries of the known world. Their journeys have prompted them to cross oceans, continents, mountain ranges, rivers, and valleys. Yet the heavens eluded them. The Greeks named the stars to give them purpose and place. Orion, Ursa Major, Scorpius, to name a few. But space, that vast, unexplored domain, remained the last frontier for centuries. And then, through imagination, coupled with science and technology, we took to the skies. With each discovery, we see ourselves, our fellow human beings, and our Earth with new eyes. From sailing ships to spaceships, exploration has always been driven by people developing and applying the latest in science and technology. And in the process, these advancements enlarge our humanity, commonality, and great human potential. Since the earliest days of the United States space program, Utah State University has developed many pioneering contributions. More than a story of technology, rockets, and measurements, this is a tribute to the imagination, innovation, and dedication of those who shaped this story with their lives. More than 50 years ago, in 1957, the Soviet Union launched Sputnik 1, a 183-pound satellite the size of a basketball, with the limited capacity to beep out its location as it flew through space. But that simple satellite kick-started the era of space exploration. The United States, long a leader in technology, was immediately behind. In years to come, Americans would land on the moon, pilot the space shuttles, and explore the solar system. But first, it had to get out in front and on its feet, contending with threats such as nuclear weapons testing and intercontinental ballistic missiles. To secure American leadership, President Dwight D. Eisenhower established NASA in 1958, and the nation expected great things. But new threats from space posed strategic questions. Could incoming missiles be detected? Under what conditions? How much, if any, warning would there be? Scientists and engineers tackled these issues that called for fresh knowledge about the upper atmosphere where these threats would be identified. USU's engineering leaders, Larry Cole and D.F. Peterson, caught the vision of space exploration and created the Electrodynamics Laboratories, or EDL. Doran Baker, a PhD candidate at the University of Utah's Upper Air Research Laboratory, was recruited to lead the effort. Founded in June 1959 in the College of Engineering, EDL attracted others with the needed expertise and deep-seated commitment to the security of their country. The space race accelerated in April 1961 when Russian cosmonaut Yuri Gagarin became the first human to orbit the Earth. The United States responded a month later when Alan Shepard became the first American in space. 9 months later, in February 1962, John Glenn orbited the Earth, the first American to make such a journey. But the U.S. was still behind. Later that month, President John F. Kennedy announced plans to go to the moon. He said,
"Our leadership in science and industry, our hopes for peace and security, our obligations to ourselves as well as others, all require us to make this effort, to solve these mysteries, to solve them for the good of all men, and to become the world's leading spacefaring nation."
It was a call to arms, and Utah State University responded. Over the next decades, USU stepped up its research and participation in space projects and developed into one of the premier space programs in the nation. In the early years of the 1960s, both USU researchers and colleagues at the University of Utah developed instrumentation for more than 100 upper atmosphere experiments. Earlier, similar missions had been flown on V-2 rockets, captured from the Germans in World War II. It was an era of dramatic advancements in atmospheric science. In the minds of citizens who tracked the progress in headlines, the space race represented the ideological contest between freedom-based capitalism and communism. USU expanded its program in 1969, establishing the Center for Research in Aeronomy, the science of the upper region of the atmosphere, housing it in the College of Science. It was first led by Dr. Clayton Clark, and then by Dr. Rex McGill. It was later renamed the Center for Atmospheric and Space Sciences. In 1970, USU attracted the Upper Atmospheric Research Lab from the University of Utah and its leader, Dr. Kay Baker. It became known as the Space Measurements Laboratory. As scientific requirements became more demanding, USU responded by developing new methods for calibrating space instrumentation. Only through precise calibration could results from different missions be compared and understood. Dr. Claire Wyatt and others at USU pioneered methods for infrared instrument calibration still in use today. National defense continued to drive research. With an atmospheric nuclear test ban adopted by the United States, USU began an intense study of the aurora, providing conditions similar to those created by nuclear detonations. Scientists pressed for answers to critical questions. What would be the effect of nuclear detonations on Americans' defense systems? Could we still communicate? Could we respond? USU's sophisticated space instruments, such as cryogenically cooled sensors, provided answers. Cooling instruments to temperatures near absolute zero allowed scientists to observe new atmospheric phenomena and to detect new types of objects in space. The Space Weather Program in the Physics Department grew with the influx of many new faculty and research programs. Interest was growing in a manned presence in space, and that posed a whole new set of issues. What were the effects of charged particles on astronauts and on large structures, such as the newly proposed Space Shuttle? In 1982, the Electrodynamics Laboratories merged with the Space Measurements Lab to become the Space Dynamics Laboratory, or SDL, in the College of Engineering. This entity would become a major force in space instrumentation. In the years ahead, research groups at USU worked with NASA to gain better understanding of atmospheric chemistry and dynamics. Other milestones included development of larger and more complex space instruments. USU and SDL's international reputation for excellence grew with each successful mission. The Space Shuttle opened opportunities for students. Led by Dr. Gil Moore, the Getaway Special program sent USU student-built projects into space. This remarkable student training also expanded USU's national prominence in space research and experimentation. USU has sent more student-built projects into space than any university in the world. Faculty at USU, led by Drs. Frank Redd, Gil Moore, and Rex McGill, next focused on the potential of low-cost, small satellites to provide additional scientific information. In the summer of 1986, they organized the first Conference on Small Satellites, with 50 people attending. Now, past its 25th year, over 1,100 people participate annually, drawn from more than 20 countries. The conference continues to foster innovation and collaboration across a worldwide community. Driven by defense programs that required a growing workforce, expanded facilities, and protection of sensitive information, a portion of the SDL staff and operations moved in 1988 from the College of Engineering to the USU Research Foundation, located on what is now known as the Innovation Campus. In 1989, NASA designated USU as an official NASA Space Grant University, augmenting its land grant status and mission. As scientific demands increased, the need for better calibration of space instruments also grew. SDL's national leadership in instrument calibration expanded in 1990 as it organized the first Conference on Calibration, or CalCon, a premier conference that SDL still hosts today. In stark contrast to the conflict almost 40 years earlier that drove the creation of USU's space program, the United States and the USSR in the 1990s embarked on a unique partnership in missile defense. For several years, SDL led what was called the Ramos program, and still holds the only ongoing cooperative agreement between the U.S. and the Russian Ministry of Defense for space research. In 1994, SDL consolidated all staff and equipment at the new research building on the Innovation Campus. Utah's congressional delegation helped make it happen. In 1996, SDL was named one of 6 original university-affiliated research centers of the Department of Defense. University officials, Utah state regents, and the legislature pulled together to get this done. This high honor, still in place today, recognized SDL's singular capabilities and contributions. Always, new challenges surfaced. Manned missions in space prompted the need to measure the buildup of electrical charge, so dangerous to spacewalking astronauts. Faculty from the College of Engineering teamed with SDL engineers to develop a measuring system that still provides increased safety for spacewalking at the International Space Station. USU drew upon its agricultural expertise to pioneer advancements in growing plants in the space station's microgravity environment. Studying these tiny spaceborne gardens helped scientists further determine how future space explorers effectively and safely can grow plants. Crops in space could help supplement diets of space explorers on long missions and provide positive psychological benefits for galactic gardeners. SDL's new technologies utilizing an infrared imaging telescope for the Spirit 3 mission were tackled next. The first telescope to be cooled in space by solid hydrogen, it provided stunning new images of cold clouds of gas permeating the regions between stars. This mission also helped lay the foundation for the space-based missile defense system that protects the United States today. When the Spirit 3 MSX mission launched in April 1996, USU had solved the challenge of rapidly transmitting digital images from space to Earth by developing image compression algorithms and electronics. Armed with this new technology, SDL joined with an aerospace firm and the Naval Research Laboratory to replace aircraft film cameras with digital ones, and to transfer the imagery to the ground quickly enough to support tactical operations. When the USU SDL team demonstrated its solution for high-ranking Pentagon officials in Washington, D.C., a new age of digital imagery for the warfighter began. And USU, with its first-of-a-kind system, would forever change the way that commanders and soldiers would receive and analyze aerial imagery. In 1999 and 2000, military in the Persian Gulf conflict had tremendous advantage using the newly deployed system to respond to battlefield situations in real time. SDL's most advanced image processing and dissemination system was recently named by the Department of Defense as the standard for all imagery ground stations worldwide. SDL began in 2002 to create miniaturized sensors and associated analysis tools that would fly on small unmanned aerial vehicles called UAVs. Better imagery enables better decisions, and SDL's sensor systems have evolved and expanded to multiple types of sensing methods including visible, infrared, and radar imagery. Our military forces are beneficiaries of USU's critical contributions to their intelligence, surveillance, and reconnaissance needs. These innovations enable our troops to defend America's interests worldwide. Over the last decade, SDL and USU have stood at the forefront of science and engineering, with groundbreaking missions in missile defense, astrophysics, Earth studies, space weather, and atmospheric sciences. Advancements driven by defense priorities have also created scientific understanding and benefited many civilian space programs. One large-scale mission, the Wide Field Infrared Survey Explorer, called WISE, funded by NASA, has provided a new map of the entire universe in the infrared or thermal regime. Complicated and highly successful, the project came in on schedule and on budget. WISE has produced a stunning stream of images of comets, asteroids, stars, nebulae, and galaxies. The WISE mission has put USU and SDL in the forefront of astrophysical discussions worldwide. Using WISE imagery, scientists have discovered a Trojan asteroid synchronized with the Earth in our orbit around the Sun, and also new types of brown dwarf stars far distant from us. And that is just a beginning. With more than 2 million images captured during its mission, WISE data will continue to provide new discoveries and insights into the universe. The leadership continues. The USU SDL team recently completed a major milestone in small satellite technologies and operations. DICE, short for the Dynamic Ionospheric CubeSat experiment, launched in October 2011, a showpiece of scientific and engineering innovation, broad student involvement, and USU-wide collaboration. DICE and its successors are designed to provide real-time information about the electric fields in the ionosphere. This understanding is essential for precise GPS-based navigation information, vital to safer air traffic flow at airports, emergency response communications, and the operation of telecommunication technologies we use every day. From the dark days of the Cold War, to the technologies of today, to concerns about our planet's health, USU's Space Science and Engineering program, and in particular its people, have helped protect America's freedom and advance our quality of life. The universe is filled with histories and mysteries. As we better understand our galaxy and beyond, we will also better grasp our collective possibilities. Fantastic discoveries are yet to be made. What was once a giant leap for mankind was clearly just the beginning of our journey. Greater discoveries and greater benefits to society are yet to come from the space program at Utah State University.